Discussing about the effective stresses in soil and flow nets. So first, I'll be discussing the effective stresses in soil. So there are four basic formulas for this topic, which is the dry unit weight, moist unit weight, the saturated unit weight, and the effective unit weight. So these formulas, we have encountered this in soil compositions. So the general formula for this is the effective stress in soil is equal to the total stress minus the pore water. So the total stress is the stress experienced by the soil mass, and the effective stress is the stress experienced by the soil particles. So in this first figure, water pressure, here the area here is only contained by water, so there is no effective stress in soil, and also the total. So the pore water pressure is P is equal to the unit weight of water, which is 9.81 times the height. So at any point to the ground or the water table. So dry soil is it has no pore water pressure, but it has the total stress. Here the total stress and the effective stress is just the same. So total stress is equal to the dry unit weight, which is to be computed or given in the problem, then H at any point. So here. The third one is when the soil is moist. So here, even though it is said to be moist, the pore water pressure is disregarded. So as the same in dry soil, the total stress and the effective stress is also equal. So here in saturated soil, it has already the water pressure. So the total stress is the saturated times H at any point. And then the effective stress, which is the sigma prime is equal to the unit weight effective times H. So this unit weight effective is just the saturated minus the unit weight of water. So an example of this is a thick layer of clay underlies a sand formation having a thickness of 5 meters. The groundwater is located 2 meters. Below the ground surface, specific gravity of sand and clay is 2.65, with sand having an average void ratio of 0.52. The clay has a water content of 42%. So here is the soil. And then the problem here is, first, compute the saturated unit weight of clay. And then second is the total stress at a depth of 10 meters. So we have to solve the stress here, the total stress. Then compute the effective stress at a depth of 10 meters below the ground surface. So here, still here. So the solution goes by, first we have to get the degree of saturation, which is we have to get the void ratio. So with this we have the saturated, which means it is 100% saturated here, this area. So you have to get the the void ratio. So with the degree of saturation and the water content and the specific gravity, we can get the E, which is 1.13. And then for degree of saturation, the formula, which is Gs plus E times the unit weight of water over 1 plus E. So by this, we can get the unit weight saturated, which is 17.47 kilonewton per meter cube. So next, we will be getting the total stress. So here, we will be getting the stress here, this one, and then this one here after the groundwater table and this clay, saturated clay. So this is saturated sand and this dry sand. So we will be getting the dry unit weight first, which is the area above the water table. So by the formula of specific gravity times unit weight of water over 1 plus E, we can get the unit weight of dry, which is 17.10 kilonewton per meter cube. And then the saturated sand, which is located below the water table, we can get it, and then the value will be 20.46 kilonewton per meter cube. So by this unit weight, we can get the total stress 10 meters below the ground. So we will add up the stresses in each area. So by this, the 17.10 times 2 plus 20.46 times 3 plus 17.47 times 5, which is the total stress 10 meters below is 182.93 kPa. So in number 3, what is asked is the effective stress at a depth of 10 meters below the ground surface. So as what you can see, the groundwater table is just this area, 3 meters and the 5 meters. So there is a water pressure there. Since there's no water here 2 meters above it, so we will not be getting the water pressure there is 0. So we will be starting here. We will be minus the total stress at the total stress minus the 9.81, which is the unit weight of water, times 8. Since only 8 meters has water here, this one. So the effective stress, which is 153.5 kPa. So next topic is the flow nets. So terms. So flow line is the line along which a water particle will travel from upstream to the downstream side of the permeable soil medium. So equipotential line is the line along which the equipotential head at all points is equal. Then flow net is a combination of a number of flow lines and equipotential lines. So in order to know more, in order to get the rate of seepage from the flow net, is this. The K, which is the coefficient of permeability, and then the H is the height of the water level or the difference in water level. So if there's only one water level, then you'll be using that one. But if there's two, you will be getting the H1 minus H2. and then NF, which is the number of flow channels, and the NB is the number of equipotential line drops. So here, this is the, as what you can see, the 1 until 8 is the number of potential drops, this one, and the flow channels is to be computed by this line going up this curve. So in getting the head loss for each potential, so this one, then this one going here, this one. So to get that one, it is just the H over ND. So this one, as what I have said earlier, if you have only one water level, you'll be using that one. So here, this is the formula. So other formulas, in getting the pressure, the formula, which is the unit weight of water times H. So H here differs from every drop. So H here, this is the formula. So H here is the height of the water level. So the water minus the number of drop. So in here, so we have to count how many drop is, like here in B. So we have to count in how many drop from here. So 1 and 2. So B is at the second drop. Then after the 8H over ND. So in every number, you can see here, they differ in H. So for uplift pressure, it's the pressure at the head plus the pressure at the toe over 2 times the length of the dam. So this is just the area of a trapezoid. Since its pressure distribution appears to be like a trapezoid. So example, a masonry dam having a sheet piling cut off at a upstream and is located at a reservoir site. Using the flow net for the subsurface flow as shown, assume coefficient of permeability to 2.003 meters per meter. So compute the seepage through the foundation, determine the pressure at the heel of the dam, and determine the uplift force. So here there are four channels and 10 potential drops. So here you can solve for the seepage through this formula. So you can get this. Just input the values given. So the pressure, number 7, the pressure drop across adjacent equipotential lines is H over ND. So by this, it is 0.6 meters per drop. So here, in HA is here, this one from the hill. So this is the hill nito. So we can get it by H. So here H is equal to 6 minus 1 times 0.6. So I was able to get this by 6. So the height of the water, here 6. So minus the number of drops. So A is located here, this one. So 1. So that is the number of drop times the pressure drop across adjacent equipotential line, which was we were able to solve it by 0.6. So the height there in A is 5.4. So in order to get the pressure, it is equal to 9.81 times HA. So which is, we have already solved it. So the answer is, the pressure in A is 52.974 kPa. So here in number 8, the uplift force is to be computed. So here we have already solved the pressure at the hill. So we should also get the pressure at the toe. So from here, the HB is solved here, which is 3.6. So 3.6 times 9.81. So the pressure in the toe is 35.316 kPa. So input the values here, which is 52.97 plus 35.316 times the length of the dam, which is 10/2. So the uplift force is 441.43 kilonewton.